Hello, in this video we're in the simple linear regression setting, and we're going to show that the least squares estimates for the betas are normally distributed. Now, we've kind of hinted upon this earlier in the playlist that I have, and we'll jump right in. So our model is y is equal to this, so it's a line plus some air, so the data fluctuates around the air. And whenever we talk about distribution, we need to assume some sort of distribution here, and we use what's called the standard normal assumptions, or the normal assumptions, and that the y, or the air terms, epsilon i's, are IID normal 0 sigma squared. So the least squares estimates for beta and beta 1, and this is previous video number 2 in the playlist, was this. We called it generically SXY and SXX, and the least squares estimate for beta 0 was this. Then we went on to show in the next video, PV3, that the least squares estimates for beta 0 and beta 1 are linear in the y's, and we showed it was this. And this is it. So this is a constant, and these are independent, identically distributed normal random variables. So beta 0 is normal, and then you can generically write it like this. And don't ask me why I put a K here and an A here. Those are just random letters that I put, but I'm going to stick with it so I'm consistent from video to video. In the same way for beta 1 hat, it was linear in the y's. So instantly, we can say that beta 0 and beta 1 hat are normally distributed. And we could use previous videos, PV3, where we talk about the properties of the least squares estimate. And we could say that, the mean, it was unbiased, had this variance, and we could instantly say it's normally distributed with this mean and this variance. And the same way with beta 1. We could instantly do that. But my question to you, but what fun would that be? So let's do some derivations. Okay, so we're going to stick with this theme that beta 0 hat is the sum of ki yi, and beta 1 hat is the sum of ai yi. We want to show that the sum of the AIs is 0. We want to show that the sum of the AI xi is 1. And we want to show that the sum of the AI squared is 1 over SXX. So the sum of the AI, when we plug in AI here, and then this is not indexed, so it can come out front, and we're just taking the sum of this, but that sum is 0. So number 1 is proven. So the sum of AI xi, and we're going to jump instantly to this setting, but remember we have an xi multiplied together. So we multiply that in, and we multiply it in here and distribute the sum, so we get the sum of the xi squared. And here we get the x bar, sum of the xi's, but we divide by n and multiply by n, and we get this. And this was another form of SXX. Which those cancel and we get 1. So the sum of AI squared is this. Remember, we have to square everything. So this comes out squared and this is squared, and we're summing it. But this is SXX. So this and this are actually the same thing. So we put in SXX. One of them cancel, and we're left with 1 over SXX. Now the page 2, we're going to show that the sum of the ki's is 1, the sum of the ki xi is 0, and the sum of the ki xi squared, ki squared is this. So the sum of the ki's is this. Now we take the sum in, and this is constant. We're summing it n times. N over n is 1. We bring in the sum here. Now these terms with no index is moved out front, and it's the sum of xi minus x bar. Well, this is 0, so that leaves just 1. Now the sum of the ki xi, we take an xi times ki, and then when we multiply this in, So here we'd get xi over n, but the sum of the xi over n is x bar. And here, we take out the pieces that aren't indexed, and then so we get xi, and then when we take that sum in, we get xi squared, and then when we take this sum in, we get x bar, the sum of the xi, but we multiply and divide by n, we get this. But this was sxx, so that cancels, leaving just x bar. So we have x bar minus x bar, which is 0. Sum of the ki squareds, we square it, right, and we get this. Now let's take the sum in. Here we get n 1 over n squared, so one of the n's cancel and we're left with this. When we take this in, the pieces that are not indexed come out front, and it's just the sum of this. And then when we take the sum into here, the pieces that aren't indexed come out front, and we're left with this. Well, this is 0, and this is sxx. Oh, and there should be a squared term there. So one of them cancels, and we're left with this right here. And we're done. So now let's take that knowledge and find the expected value of x, or the beta 0 hat, the least squares estimate of beta 0. And we're going to use this linear combination, because you may have done that. You're like, oh, it is a linear combination of the y's. So now let's take its expected value. And the same thing with the variance of the least squares estimate of beta 0. We may like, oh, it is a linear combination. We know it's normally distributed, so let's find the variance. You may end up using that approach. So we take the expected value, and the expected value comes into the y, and that is the line, beta 0 plus beta 1 x 1. So now we multiply that and distribute the sum. But this sum to 1 and this sum to 0, and we're left with beta 0. So it's an unbiased estimate. Now the variance of this linear combination, now notice that the yi's are independent. So when we take this variance, then there's no covariance between the two. And we have to bring out the ki squared. And the variance of yi is sigma squared, so it comes out front because it's not indexed. The sum of ki squared is this. Right? So this is the same as what we got before. So the expected value of the least squares estimate for beta 1 in linear form is this. The variance, of course, we're going to take it in this term. So the expected value comes in. The expected value is the line. We distribute. This is 0. This was 1. We're left with beta 1. The variance, when we bring it into this sum, there's no covariance between the y's because they're independent. So and then we had to factor out the xi squared. This is sigma squared, so then it can come out front. And the sum of the ai squareds was 1 over sxx, which is this. So therefore, beta 0 is normally distributed with this, the same as we got on page 1. Beta 1 is normally distributed with this, same as page 1. And so that's the proof. Now as a bonus, we're going to show that the sum of the ai ki is this. And it's a bonus because I really wanted to end right here, but I have paper left. So I'm like, let's add in some bonus calculations here. Let's show it's this. So now you take the sum of ai and ki right here. I mean the product. So when we multiply this to this one, we get this. And then we multiply this to these two terms, and we get this. Right? So this sum is 0, so that goes away. And this is sxx, so one of those cancels. Well, this cancels with one of those, leaving minus x bar over sxx. So now let's find the covariance between our two least squares estimates. We put it in linear form as this. Now the sum we can bring out front, right? And we get this. Now the ki And I switched index to illustrate that you have to do that. They come out front, which is this. We have the covariance of yi and yj. But when they're not equal, this covariance is 0. That's one of the assumptions. So whenever I and j are not equal, it's 0. So they don't add to the sum. So we just make them both say I. So when we sum from 1 to n, ki, ai, covariance of yi, and this is the variance of yi, which is sigma squared. So then it can come out front. And this sum is minus x bar sxx times sigma squared. And this is what we showed to be the covariance in an earlier video. All right, well, that's all I have for today. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks, bye.